Welcome to today's lecture for energy balances on non-reactive phase change processes. We already looked at some of the fundamentals associated with such processes and we solved a couple of simple example problems. Today we will have a tutorial sessions. We will look at problems which are a little more complicated, try to address them from all different angles so that we can actually get a full feel for how these problems need to be solved. A mixture that contains 46 weight percent acetone and 27% acetic acid and 27% acetic anhydride is distilled at pressure 1 atmosphere. The feed enters the distillation column at temperature of 348 Kelvin at a rate of 15,000 kilograms per hour. The distillate, which is the overhead product, is essentially pure acetone and the bottoms product contains 1% of the acetone which is sent through the feed. The vapor effluent from the top of the column enters a condenser at 329 Kelvin and emerges as a liquid at 303 Kelvin. Half of the condensate is withdrawn as the overhead product and the remainder is reflexed back to the column. The liquid leaving the bottom of the column goes to a steam heated reboiler in which it is partially vaporized. The vapor leaving the reboiler is returned to the column at a temperature of 398 Kelvin and residual liquid also at 398 Kelvin constitutes the bottoms product. A flow chart of the process and the thermodynamics data of the process materials are given here and based on that you are expected to calculate the molar flow rates and the composition of the product stream, the condenser cooling requirement and using the overall energy balance to determine the reboiler heating requirement QR, and if the reboiler heat is provided by the condensation of saturated steam at 10 bar, at what rate should the steam be fed. So now we have multiple things that we need to calculate. So we have the flow chart given and the thermodynamic data given. Let us look at how we would go about solving this problem. The first part of the problem is only material balance and it is a reasonably simple material balance that we need to perform. Before we start performing the material balance calculations, let us first label all the unknowns. We have all the information about the feed stream. We know that the column overhead basically contains only acetone vapor which is condensed and half of it is sent back as recycle and the other half is removed as the distillate product. So the column overhead, let us assume that it is 2 N1 kilograms per hour. So this would be a vapor phase and you have a distillate product which would be N1 kilograms per hour which is a liquid product and you would also have N1 kilograms per hour of recycle which is also a liquid sent back into the system. We also have been given the temperature conditions which is 329 Kelvin for the column overhead and 303 Kelvin for the distillate product and the recycle stream. So the bottoms enters into a reboiler and you have a bottoms product which is recovered and this bottoms product contains 1% of the acetone which is fed to the system. The rest is acetic acid and acetic anhydride at 398 Kelvin. So let us call this as contains N2 kilograms per hour of acetone and N3 kilograms per hour of acetic acid and N4 kilograms per hour of acetic anhydride. So these are the mass flow rates of these components which are leaving the system through the bottoms product. Now let us perform the required material balance calculations. The first information that we have directly is 1% of the acetone fed to the system is actually recovered through the bottoms product. So which means we can calculate N2 directly. So N2 is equal to 0.01 times 0.46 which is the mass fraction of acetone in the feed times the mass flow rate of the feed which is 15,000 kilograms per hour. So therefore you get N2 as 69 kilograms per hour. Now we need to calculate how much of acetic acid and acetic anhydride are actually leaving through this stream. So we need to write an acetic acid balance. Acetic acid balance would be input equals output which would be N3 equals 0.27 times 15,000. As acetic acid and acetic anhydride are leaving only through the bottoms product for the overall system, this calculation is simple and we can get N3 as 4050 kilograms per hour. Similarly, writing an acetic anhydride balance, we would be able to calculate the N4, which is 0.27 times 15,000 equal to 4050 kilograms per hour. So, from this we can calculate what the bottoms product is. So, bottoms product is basically the summation of these masses, which is 4050 plus 4050 plus 69, giving a total mass of 8169 kilograms per hour. Using the total mass balance, we can actually calculate the distillate product also. Distillate product can be calculated here. So, what we need to do is the total mass balance would be 15,000 equals distillate plus products, sorry, bottoms. So, now we already know the bottoms is 8169. So, we can calculate distillate as 6831 kilograms per hour. So, with this we have the mass flow rates of the distillate and the bottoms product, and also the composition of the bottoms product can be identified because we know the individual components and the mass flow rates of the individual components. So, the bottoms product composition would be 69 divided by 8169 times 100% for acetone, and it would be 4050 divided by 8169 times 100% for both acetic acid and acetic anhydride. So, you can calculate this and the values are 0.8% acetone and 49.6% acetic acid and acetic anhydride. With that, we have performed the required material balance calculations. We can now move on to the second part of the problem. In the second part of the problem, we have been asked to calculate QC dot, which is the cooling requirement of the condenser. So, this QC dot needs to be calculated. For identifying QC dot, we can actually use the condenser as the system and perform energy balances. So, what we have is acetone, which is coming in as vapor at 329 Kelvin, is getting condensed to form acetone liquid at 303 Kelvin. So, this is the overall process. Looking at the thermodynamic data provided, we have that the heat of vaporization for acetone, the standard heat of vaporization for acetone at 329 Kelvin is given, which means we can use that heat of vaporization for performing these calculations. So, this can actually be broken down into two steps, which would be acetone vapor at 329 Kelvin going to acetone liquid at 329 Kelvin and then getting cooled further to form acetone liquid at 303 Kelvin. So, this would be the condensation process where you have the delta H cap V can be used, and this would be a change in temperature where you can use integral Cp dt. The total change in enthalpy for this process, which will be calculated as delta H cap would be, so this is the total change, this would be the total change in the specific enthalpy of the process for the condenser. So, this would be equal to minus of delta H cap V. So, because it is a condensation process, we will be using the negative of heat of vaporization plus integral of 329 Kelvin to 303 Kelvin Cp of acetone liquid dt. So, using the Cp of acetone liquid we would be able to calculate these values. So, we know that the Cp of acetone liquid is 2.3 kilojoules per kilogram Kelvin. So, using that value we can directly calculate what this would be. So, this is minus 520.6 plus 2.3 times minus 26. So, your H cap value is equal to minus 580.4 kilojoules per kilogram. So, QC can be obtained using simple energy balance. So, this is an open system. So, the equation would get simplified to form QC dot equals delta H cap. So, delta H dot. Delta H dot would be equal to mass flow rate times the change in specific enthalpy. So, the mass flow rate is 2 times N1 which is 2 times 6831 times minus 580.4 which would be in terms of kilojoules per hour. So, QC dot is equal to minus 7.93 times 10 power 6 kilojoules per hour. So, the rate of cooling which needs to be done for this system which is the condenser is minus 7.93 times 10 power 6 kilojoules per hour. So, we have the negative sign because it is a cooling process where heat is being removed from the system. Now that we have performed the calculations for the second part, we can move on to the third part where we have been asked to calculate the Q dot R which is the heat supplied to the reboiler, and this has to be done using the overall system as the system to be studied for energy balance. Let us look at the overall system. So, the overall system would basically have acetone liquid at 303 Kelvin leaving the system, acetone liquid at 398 Kelvin leaving the system, acetic acid and acetic anhydride at 398 Kelvin leaving the system. So, we need to have these streams as the outlet streams, and we would have an inlet stream which would be acetone, acetic acid and acetic anhydride liquids entering the system at 348 Kelvin. We can choose reference states either as the inlet or the outlet conditions. For these calculations I have used the inlet condition as the reference states. So, the reference state for this problem would be 348 Kelvin and liquid as the phase. So, now let us write down all the components. So, here we have acetone which is leaving in 2 different streams at 2 different conditions. So, we will write these separately so that we can calculate the specific enthalpies for these 2 things separately. So, the substances we would have would be acetone liquid which is at 303 Kelvin and acetone liquid at 398 Kelvin. You also have acetic acid which is liquid and acetic anhydride which is also a liquid leaving the system both at 398 Kelvin. So, the inlet conditions have been assumed to be the reference state. Because of this, all the enthalpies associated with the inlet streams would be equal to 0. So, we do not have to worry about the inlet stream enthalpies for this calculation. So, we have to however account for the outlet enthalpies. So, the outlet enthalpy H cap out would have to be calculated. Now, we need to identify the flow rates for the individual components which have been entered in the enthalpy table. So, we have 6831 kilograms of acetone liquid leaving at 303 Kelvin and 69 kilograms of acetone liquid leaving at 398 Kelvin, and we also have 4050 kilograms of acetic acid and acetic anhydride liquids leaving at 398 Kelvin. So, now we need to calculate the specific enthalpy changes for each of these processes. So, we have acetone liquid at 348 Kelvin going to acetone liquid at 303 Kelvin and acetone liquid at 398 Kelvin. We have acetic acid liquid from 348 Kelvin going to 398 Kelvin and acetic anhydride liquid from 348 Kelvin goes to 398 Kelvin. So, now we need to calculate these enthalpies using the Cp values that we have. As all these components are simple enough to calculate, we should just be able to directly use the Cp values and fill out this table. So, please go ahead and do these calculations. I will give you the answers which I have here, which is minus 103 kilojoules per kilogram and 115 kilojoules per kilogram and 109 kilojoules per kilogram and 113 kilojoules per kilogram. So, the first acetone liquid alone you have cooling from 348 Kelvin, which is the inlet, to 303 Kelvin, which is the outlet. So, because of this you have a negative change in enthalpy. The other ones you are actually increasing the temperature by 50 Kelvin. So, you end up with values which are positive. So, we can calculate, so now we can calculate the total change in enthalpy using this, and we would have to plug it into the general energy balance, the overall energy balance equation to get QR. So, assuming that there is no energy which is being used in the distillation column, we will only account for QR and QC, because those are the only terms which have been given to us as the terms where heat is being supplied. So, using that assumption, we will calculate Q dot as QC dot plus QR dot, and fitting it back into the general energy balance equation, this would be equal to delta H dot. So, now we can have QC dot plus QR dot equals sigma of N out H cap out. So, as all the values for H in are 0, we can ignore the inlet stream and we will be able to perform calculations using this. So, we would get QR dot as minus QC dot plus sigma of N out H cap out. So, this value comes out to be 8.13 times 10 power 6 kilojoules per hour. So, this is the amount of heat, rate at which heat needs to be transferred to the reboiler, so that you have the process according to the parameters given. So, with this we can move on to the fourth part of the problem, where we have been told that the heat for the reboiler is supplied using steam. So, it is coming in as steam which is saturated at 10 bar. So, using the heat of vaporization for steam which is saturated at 10 bar that can be obtained from the steam tables, we can calculate how much would be the mass of steam which is required for generating that amount of energy. So, just by condensation, using the steam tables we can identify the enthalpy associated with condensation or vaporization of saturated steam at 10 bar as 1999 kilojoules per kilogram, and so this means condensation of 1 kilogram of steam which is saturated at 10 bar would generate close to 2000 kilojoules of energy. So, to calculate the mass of steam required, we would have to calculate QR dot divided by delta H cap V, which would be roughly equal to 4070 kilograms of steam per hour. So, by condensing 4070 kilograms of steam which is saturated at 10 bar per hour, we will be able to generate the amount of heat required by the reboiler. So, this gives us a way to calculate the energy balances, and we have tried to use multiple concepts which we have learnt over the last few lectures to apply here. In the next lecture we will talk about similar calculations, however, we will look at a closed system. Until now all the calculations that we have performed are for open systems. We will look at how energy balances can be applied for closed systems in the next lecture. Thank you.